Okay, so now let's look at the molecular orbital picture of the enolate. And before we go there, let me just draw out a simpler system that we can try and understand first before we get there. Okay, so just to remind you, this is the enolate that we're looking at. And so parallel structure that we are all familiar with is the allyl group. So if I start with this kind of a system, let's say basically this is an olefin attached to a methyl group, and if you pull out H plus from this, then you end up with a system such as this. Okay, this is the allyl anion. Okay, now we want to look at the molecular orbital picture of this, and before we do that, let's just draw out its resonance form, which is as follows. So you have a negative ion on the terminal carbons. Okay, so therefore this is represented by us many times as a delocalized negative charge on these three carbons. Now let's look at the molecular orbital picture. Okay, so the molecular orbital picture is as follows. So you have energy over here, and so basically you have three p orbitals, and if these three p orbitals combine in a favorable manner, so you get the lowest energy picture with the orbital, which is this. So they are all of the same signs. I'm going to call this as psi 1, and now psi 2 would be the orbital wherein you have mixing going on, but there is a node. So the way it's drawn is the following, right? And so this is the picture of how it's shown. And now the third orbital, when you mix it, the third orbital that is going to be produced is the orbital where the signs are actually opposite to one another, which produces a unfavorable situation. So that would be psi 3. Okay, and now in the case of the allyl anion, you have 2 electrons from the pi bond and 2 electrons from the negative charge. So the way we would draw it is this. So these two are actually filled. Okay, so please pay particular attention to this, because this orbital is the HOMO, the highest occupied molecular orbital, and this is the LUMO, which is the lowest unoccupied molecular orbital. Okay, so as we discussed earlier, in terms of reactions, when a negatively charged species reacts, the most important orbital that we would like to consider is the highest occupied molecular orbital. And when a functional group is acting as an electron acceptor, then the orbital that we need to consider is actually the LUMO, the lowest unoccupied molecular orbital. So therefore, the electron density according to this map, according to this molecular orbital picture, suggests that the maximum electron density is at the terminal carbons as shown here. Okay. Now, there is some experimental evidence that supports this claim. So, for example, allyl lithium is a commonly available reagent, and when we record the NMR spectrum of this is going to dissociate to give this anion and lithium plus. And so, if we record a carbon 13 NMR spectrum, then what we see is actually a very interesting picture. So if I start with propene, then I would get the carbon 13 NMR spectrum. We would get signals such as this, where this is 19.5 ppm, this is 134 ppm, and this is 116 ppm. Okay, so this is what you would get if you just record propene's NMR spectrum. And if we take the NMR spectrum of methyl lithium, then we see a peak at minus 15 ppm. Okay, so therefore all of these values are in ppm. So therefore this methyl lithium pushes the value or the chemical shift value all the way to much below 0. And so when we record the NMR spectrum of this allyl lithium, then what we get is we get only two signals. We would expect essentially three signals, but we see only two signals. One is at 147 ppm and the other one is at 51 ppm. Okay, so which is assigned to this delocalized anion as shown here. And the interesting thing here is that it supports our molecular orbital picture in a couple of ways. One is that because you have a resonating form over here, that is between this, the negative charge spends time on this carbon as well as this carbon, and therefore it is going to be delocalized. You see only two signals here, as opposed to what you would expect would be three signals if it is spending time, if the negative charge is localized only to one of the carbons. Okay, and the second thing here is that once the carbon has a negative charge, you see that the value of the chemical shift goes down substantially. Okay, so for a normal olefin, what we would expect is the value between 120 and 130, but we actually get a value of about 51. Okay, so this substantial jump in the chemical shift suggests that this carbon actually has a strong negative charge. Of course, it doesn't have a full negative charge, it would have a strong partial negative charge. So I will repeat this concept once again. There are 2 points about this experiment. The first one is that the two ends of the carbon are actually the same because you get only two signals when you record the NMR spectrum of allyl lithium. And this tells you that there are only two carbons, two distinct types of carbons. And so one is this peak at 147 and the other one is 51. Okay. Point number two, most of the negative charge is actually localized in the two corners. So that is two terminal carbons, which would be 51 and 51 ppm. And this tells us that the most reactive center in this anion is actually the terminal carbon. So with this background, let's now look at the enolate, the picture of an enolate. Okay, so just to recap, an enolate is generated when you react base, for example, with the ketone, and so this is the carbanion, and this is going to delocalize or is going to push its negative charge into the oxygen, and you're going to get a enolate anion. Okay, so now if I have to construct a picture, molecular orbital picture for this, then what I would need to do is actually, let me just juxtapose these two pictures so that it's easy for us to understand. So this is the energy. So for the allyl anion, the way we understand it is that we're only considering the LUMO. So there are 3p orbitals which are mixed and these are shaded, and this is your psi1, and the next one is this where you have a node. Okay, I think all of you know what a node is. So this is psi1 and this is psi2. Okay, so now when these electrons are filled, you get a system like this where you have this allyl anion. Now if I have to look at the same picture for the enolate, what ends up happening is that because oxygen is more electronegative, this brings down the energy. So when compared to an allyl anion, so the psi2 and psi1 would be lower in energy compared to the allyl system. Okay, so this is because of we have already looked at it earlier. When you have an electronegative atom bound, then it's going to lower the energy. Okay, now being an electronegative atom, we've also seen previously that this distorts the orbital picture substantially, and so the picture is going to look something like this, where you have a much larger lobe for oxygen and a smaller lobe for carbon. You need to look at your textbook for the more accurate picture, but I'm just drawing this so that you guys understand. So this is the oxygen and this is the carbon. Okay, so this would be my psi1. And now when I come to psi2, which is the next highest orbital, we actually have a larger lobe in the carbon and then much smaller lobe in oxygen. And so therefore the orbital over here is much smaller compared to the oxygen for psi1. Okay, so these are the two molecular orbital pictures. Okay. Now, so therefore, there are two important takeaway points. Number one point is the oxygen is more electronegative, so therefore it brings down the energy. So if you see, they compare the Psi2 of the allyl anion versus the Psi2 of the enolate, the energy of the enolate is substantially is lower. The second one is that the electron distribution is actually happening across all the three atoms, and in the Psi1 you have a larger lobe for oxygen, and in Psi2 you have a larger lobe for carbon. Okay. Now this I'm going to redraw in the next page because I want to discuss this a little bit. So let me look at the Psi2 because that's an important orbital for us to look at. So when I draw this out again, I'm just drawing it out again for us to understand this. There's a very small component to the center carbon, but this is my oxygen and these are the two carbons. Okay. And the way we have shaded it is like this. So this is my Psi2. Okay. And as you recall, this would be the highest occupied molecular orbital, and therefore this plays an important role when we are looking at how this is going to react. All right. So now, in terms of the reactive orbitals, we found that the allyl anion, both the carbons are equally reactive because the size of the lobe on both the carbons was identical. But what we also figured out was that the center carbon is not going to react because there was no orbital there for it to react in terms of a electron donor. Okay. So in an enolate, you see that the size of this lobe, let me just redraw this so that to make it a little clearer. So you have two carbons and one oxygen, but just to be clear, this is the carbon, this is the carbon, and this is the oxygen. And so the size of the lobe here is substantially larger on the carbon. I'm just drawing it very large just to make the point. And there's a very small component on this carbon. And this carbon, the terminal carbon, is going to play an important role in determining how reactions actually happen. Okay. So now what we can suggest is that the two reactive centers on this enolate are these two, that is this carbon and this carbon, and the way in which these reactions occur is going to be different, okay, when compared to an allyl anion. Now when we actually do an experiment, we will find out, if we can reason this out. When we do an experiment, for example, when I take acetone and react it with some base and add acyl chloride, okay, the product that I get is actually O C double bond O CH3. The product is actually the one that gives you the O acylated product. Okay, so let me just erase this and redraw it so that it's clearer. O C double bond O CH3. Okay, so this is the product that I get, right? Whereas when we react base and I react it with, let's say, ethyl bromide, okay, the product that we obtain is this. Okay, so where this ethyl group has come from this ethyl bromide, right? Now the way we want to understand this difference in reactivity is through the molecular orbital picture. Okay, so the reactions that are dominated by orbital interactions, these are occurring at the carbon. Okay, and this is somewhat reasonable because we realize that in the enolate, the largest orbital of the HOMO was actually located at the carbon. So just to recap, so this was the largest orbital, and then there was a smaller orbital, which is a small orbital here. So this is the way in which we would draw this picture. And whereas if you see the oxygen, which is over here, the oxygen reacts when there is a reaction that is dominated by charges. Okay, so when the O minus has a very significant amount of that is the oxygen being the more electronegative atom, has a stronger charge component on it, and therefore the reactions which are dominated by charges and electrostatic interactions. So electrostatic and charges, these are actually reacting at the oxygen. Okay, so therefore a substantial difference or an important difference between the enolate and the allyl anion is that the allyl anion is very symmetric and both the ends are equal, and so therefore there's no difference in which end reacts, whereas in the enolate there are going to be differences that are going to come in, and one important difference is that the oxygen being electronegative has the greater charge on it, and so therefore reactions which are dominated by charges by electrostatics actually occur at the oxygen, whereas reactions which are dominated by orbital interactions, being the HOMO of the enolate has a larger lobe at the carbon, and therefore this dominates the reactions that occur at the carbon center. Now, we will discuss this in more detail in the coming chapters when we look at how to generate enols and enolates. But right now, it's important for you to recognize that there is a difference between the carbon and oxygen in terms of reactivity. All right. So now let's summarize the various aspects of enol and enolate chemistry. So if we start with cyclohexanone, and for cyclohexanone, we could draw out, this is the keto form, which is just cyclohexanone, and the enol form would be in the following manner. This is the OH, and the enolate is this. Okay, so this is the enolate, this is the enol, and this is the keto. Okay, so these terms I think we should all get quite familiar with, and once these are clear, then we don't need to worry too much, because rest of the course we will be coming back to these terms again and again. Okay, now as you know, carbonyl compounds, there are several varieties of carbonyl compounds. So one variety of carbonyl compound that we all know is the ester. So a typical ester is shown in the following manner: C double bond O, OMe. Let's say I take a methyl ester, and now when I add a base to this, OMe minus. Okay, so when I add a base to this, then what can happen is that this hydrogen over here, this negative charge can come in, attack here, and it can generate a enolate, O minus, OMe. Then there is a double bond. Okay, so this enolate of a carboxylate anion can be generated under these conditions. And now you can ask me the question, what happens if the methoxide actually attacks the carbonyl? Okay, so let's consider that option now. So when OMe, if the methoxide attacks here instead, which it can certainly do, then it's going to produce the tetrahedral intermediate that we are quite familiar with. So O minus, and then there's a CH3 over here. And now this can come in here and kick out this methoxide, and it is basically going to regenerate the ester. Okay, so using the right base for generating the enolate is very important. Now you can also think about the possibility of using hydroxide, which I accidentally drew at the beginning of the slide, the previous slide. But what happens if you use sodium hydroxide instead of methoxide? Then what can happen is you have a competition between two things. One is that it goes here, and the other one is it goes to the alpha position. Now let's first consider this. It goes here, and then it produces the tetrahedral intermediate, OMe, right? And you have OH. Okay, now when it comes back in, it can do two things. It can either kick out methoxide or it can kick out hydroxide. And if it does kick out the methoxide, then what it's going to produce is it's going to produce a carboxylic acid. Okay, and when this carboxylic acid is produced, you all know that in the presence of a base, it's going to very quickly give you the carboxylate, which is actually not going to further react. Okay, now therefore this reaction is going to be favored when you use a nucleophilic base such as hydroxide ion, and so you're going to get the carboxylate ion. Right, now the second possibility of picking up alpha hydrogen can happen, but once it picks up the alpha hydrogen and produces the enolate, that's going to go back and produce this again, and this reaction is going to dominate because of the formation of the carboxylate ion. Okay, now when we look at the next case, which would be the formation of amides or a formation of an enolate from amides, so let's consider that. So you have CH3 C double bond O NH2, I'm sorry, it's not NH3, and so if you have NH2 here, and now when I expose this to a base, let's use sodium methoxide again as the base, OMe minus. So now when I expose this to this base, now the methoxide can again do a couple of things. This is indeed a proton that can be picked up, and you can generate the enolate, as we are quite familiar with, right? And however, there is a problem here. The problem is that this NH2, actually, this hydrogen is quite acidic. You might have studied about this in the previous semester. And so what instead happens is, instead of producing this kind of an enolate, what actually may end up happening is that you have NH, and this methoxide now attacks here, and it produces a fairly stable amide anion. Okay, so you have C double bond O NH minus. Okay, this amide anion, one of the reasons why this is stable is it can delocalize, and it can produce the resonance form as shown here, which is basically O minus double bond NH and CH3. So because of this possibility, or rather, we understand the stability of this amide ion by invoking this concept as shown here. Okay, so amides are not very conducive to producing enolates because of their, or at least amides with an NH2 on it, they are not conducive to producing an enolate because of the formation of this kind of a anion. Okay, now the last thing that we need to look at, or one of the last things that we need to look at, is what happens when you react a ketone with an amine. Okay, so again, this is something that many of you are familiar with, but I will quickly revisit it. So when I take a aldehyde and react this with, let's say, aniline, pH NH2, okay, and now what we end up getting is an imine, which I'm hoping that all of you are quite familiar with. But let me just go through a little bit of background here. So when you add these two reagents together and you add a catalytic amount of H plus, okay, so what you can suggest is that this NH2 is clearly the better base, so it's going to pick up a proton, and it will be in equilibrium with pH NH3 plus. Okay, but since there's a small amount of acid, you can imagine that once in a while this picks up this proton from pH NH3 plus perhaps, and it gets protonated. Okay, so once it gets protonated, you're going to produce OH plus. Okay, so this OH plus is actually quite a nicely activated carbonyl substrate, and now your amine, which is in fairly large concentration compared to the proton, can attack, and you will expect to get this kind of an intermediate where you have OH and you have NH2 pH, and keep in mind that this positive charge is still here. Okay, so now let me draw this intermediate up in the next slide. So NH2, pH, OH, and you have a hydrogen here and we have an isopropyl group here. Okay, so and this positive charge remains over here. Okay, now what can happen is that you can have a transfer of this proton from this amine cation to the hydroxyl group, and you will end up getting this protonated water species. So you have NH, pH. The remaining groups are the same. Okay, so you get a positive charge over here, right? Now, what can happen is that this lone pair on nitrogen can now come in over here and kick out water. As you know, water is an excellent leaving group. And so if it does this, then you get your imine. Okay, so this is what happens when you have a primary amine. So this is called the IMINE. Okay, so it is not imine, it is imine, and this imine is a very important intermediate that we will look at later. Okay, but just like a carbonyl compound, this imine actually has alpha hydrogen. Okay, so we have been discussing about how enolization etc. can happen. So it is entirely possible that this sort of undergoes some sort of a tautomerism, and it can produce NH, pH, and it can produce this kind of a intermediate. Okay, so this intermediate is called the enamine. Okay, so just to revise this concept, so you have the formation of an imine, which is shown here, and then you have the formation of an enamine. Okay, again, you can go back to your textbook. This is in the formation and reactions of enols and enolates, and you can go back and look at it. Okay, so this is what happens when we start with a primary amine. But now what happens when we use a secondary amine? Let's look at that, and that should conclude the lecture on this topic. So what happens, let's say the example that we can take is this, right? So this is pyrrolidine, and so when pyrrolidine basically reacts with this aldehyde, what the product that you get is going to be, if I extend the same logic of the production of the imine, then you're going to get an imine such as this IMINE. Okay, but the interesting thing here is that you have a proton that is going to be enolizable, and so if you again push electrons, you're going to get the formation of fairly stable enamine. Okay, all right, so essentially what happens is that when you start with the ketone, you get an enol, you get an enolate. When you start with an ester, you can get an enolate that is derived, provided you use the right kind of base. If you use hydroxide, for example, you're not going to get the enolate, but you end up getting the carboxylate. And amides are a case where you don't have the formation of the corresponding enolate, but instead you get the amide anion. But you can generate imines and enamines by using carbonyl compound and the corresponding primary or secondary amine. And when you use a primary amine, you end up getting a mixture of both the imine and enamine. And generally speaking, the imines in this case are more stable. But when you use a secondary amine such as pyrrolidine, the major product that you would end up getting is the enamine. So with this background, I think we can now move on to some of the reactions of enols and enolates.